Good day. For those of you who do not know us, we're the instructional staff for Ieee 150, Professors Hiran Patel and Verna Dietl, and Douglas Harder. In this topic, we're going to quickly cover the floating point primitive data types. In this lesson, we will review what we've already seen about floating point numbers, review scientific notation, consider storing approximations of real numbers using fixed precision scientific notation, consider some simple examples of arithmetic, look at weaknesses, and describe the document IEEE 754. Now, up until this point, we have used the double data type for storing approximations of real numbers. This is actually short for the longer name double precision floating point data type. So this is just abbreviated as double. There is also a single precision floating point data type, and it is called float. Now, each of these only stores approximations to real numbers, and the double stores approximately twice as much precision as the float. Now, recall from secondary school, scientific notation allows you to write numbers clearly and succinctly. In the left-hand column are numbers stored using the usual fixed point notation, where you essentially have to store a lot of extra digits perhaps, whereas on the right-hand side we see the corresponding scientific notation. Once again, the scientific notation is much more useful than the fixed point notation because you simply have to look at the number to see, in this example, the significans or the significant digits, a base, and an exponent. And that gives you information as to what the significant digits are and the relative magnitude. Now, the number of decimal digits normally displayed in scientific notation shows the precision. So here in the last case, we see that we have an approximation of pi to 18 significant digits, or a precision of 18 digits. Without going into too much detail, each data type has a maximum precision it can store. So for example, the float, which is stored using 4 bytes or 32 bits, can hold approximately 7 decimal digits of precision. The double, which occupies 8 bytes or 64 bits, can store approximately 16 decimal digits of precision. Now, for engineering applications, you should always use double. There's only one situation where you may consider using a float, and that is in computer graphics. That is because the resolution of the Mark I eyeball is actually not that good. So the float is sufficiently precise for that application. In almost all other applications, you should be using a double. Now, this fixed precision does lead to some weaknesses. For example, if the exponent is too large or too small, the number cannot be stored. The minimum positive value that can be stored with a float is approximately 1.4 times 10 to the negative 42, whereas the maximum positive value is approximately 3.4 times 10 to the 38. You can see the same ranges for the double, except now the double can store a much larger range, with numbers as small as 5 times 10 to the negative 324 and 1.8 times 10 to the 308. These are approximations again because they are actually stored using binary, not decimal. Also, you may recall with integer data types, you may have carries, overflows. If you divide by 0, you actually can terminate the program you are running. However, with floating point representations, there are actually special values for plus or minus infinity. so there's no overflow occurring. There are also other values such as not a number to represent calculations such as 0 divided by 0, which you learned in secondary school as being indeterminate. Similarly, if you try to subtract a number that's too large to represent from another number that's too large to represent, you have no idea what that value is, so that will be calculated as not a number. Also, numbers too small will be represented by plus or minus 0. So a positive 0 does not actually mean 0. It means a positive number that is either 0 or positive and so small it cannot be represented by the current data type. Similarly, negative 0 means that it is too small, negative, but too small to be represented, again, by either data type. Now, fixed precision also does tend to have some weaknesses. It can happen that you can add two numbers together, such as x plus y, and the result can leave x unchanged even if y is not 0. So if y is too small relative to x, it can happen that x plus y leaves x unchanged. If x and y are almost exactly the same, it can happen that there are issues or loss of precision if you must perform a calculation such as x minus y. Also, associativity does not work with floats. So if you add y and z together and then add x, you may get a different answer than if you added x plus y together first and then to that result added z. Now, this is not going to be covered in this course. However, you will see all of these issues in your courses on numerical analysis. Now, floating point numbers are meant to represent real numbers in the computer, and thus you can perform the following binary and unary operators when working with doubles and floats: plus, minus, times, divide, and the neutral and negation operators. You can also use the automatic assignment operators associated with the binary arithmetic operators above. However, you cannot use the modulus operator, and you cannot use bitwise or bit shift operations with any local variables declared to be of either type, double or float. Now, just an interesting issue, IEEE 754/2008 is the most recent standard from IEEE for floating point numbers. Originally written in 1985, that is IEEE 754/1985, this document specifies the representation of both float and double. What's very cool is this has become an industry standard. That means it doesn't matter which programming language you're using, your calculations will always end up having the exact same result. The only thing that matters is the quality of your algorithms. Unfortunately, Java is not IEEE 754 compliant, and Kahan and Darcy have an interesting article, How Java's Floating Point Hurts Everyone Everywhere. So following this topic, you now know that floating point numbers are stored using fixed precision scientific notation. You understand that there are issues and that they are not perfect, but this will be covered not in this course, but in a course on numerical analysis. You also know that the float data type is insufficiently precise for most engineering computations, and the one exception is graphics. And you understand the idea of having standards associated with programming features such as floating point numbers, specifically which are described by IEEE 754. Here are some references, acknowledgements, the colophon, and a disclaimer. Cheers!